Okay, so this is another predominant species, and what I want to point out in these problems is when you're doing polyprotic acids or bases, the easiest way to deal with them is to think of them um, like a titration curve. Okay, of a polyprotic acid. So if you look at a titration curve, you have this repeated. There we go. This repeated pattern that shows up, and that is that you have the pure acid. As you add more base to it, you're going to enter a buffer region. Right there is your buffer. As you add more base to that, you destroy your buffer, and in this case, you actually reach your equivalence point where you've neutralized all of that original acid. Keep in mind that this point right here, this is half the equivalence point. And so that would mean that you are halfway through using up all your acid and turning it into base. What that means is that at this equivalence point, the half equivalence point, your pH would equal your pKa. Also, at this point is when you have an equal amount of acid and base. And so, anytime you have a mixture of acid and base, then you have any significant amount of the acid form and any significant amount of the base form, and they're together, then you can always use that as a buffer solution. Another way of saying that is you can use the Henderson-Hasselbalch equation, which makes your life a lot easier. This is, of course, only if you have a significant concentrations you're talking about, larger than your pKa. If you have a Ka of 10 to the negative 4 and your concentrations are 0.1, 0.2, 0.3, something like that, then you're fine. That's going to work really well for the Henderson-Hasselbalch equation. It's only when you start reaching more fringe cases where you have much, much smaller concentrations or much, much larger Kas, they have to start worrying about the Henderson-Hasselbalch equation not actually being correct, because the assumptions you make in that equation would fall apart. Uh, Ask me more about it sometime if you'd like to learn more about that. But so at this point right here, you're going to turn all of this first acid form. You're going to lose all of the first H plus, that Ka1, and form what is the conjugate base for this portion, but will be the acid for the next leg of it. And so that means, for example, like carbonic acid, you would have H2CO3. It goes and makes more and more HCO3 as you go along. This point, it would be essentially all HCO3. And then after this point, it's going to start losing that second H plus. And that's going to mean that you're going to have a mixture. At this first leg, it'll be mostly HCO3. And at the next leg, after you reach this midpoint and go past it, it'll be mostly the CO3 2 minus species until it reaches this point right here, in which case it's all the CO3 2 minus species, and you have you're completely the basic form, the most basic form. By the way, it again flattens off because whatever OH minus you put in there, eventually it reaches a peak where you have essentially pure base, and so it doesn't make any difference whether you put more in or not. Anyways, so what we have here is we have carbonic acid, and we have its pKa's that are actually listed right here, and it actually shows you the species on each side of it. And right here you have the H2CO3, right here's the HCO3 minus, and right here's the CO3 2 minus. These points right here, these pKa's, these would be your midpoints. So anything lower than it is going to have more of the acid form. So a pH of 6, for example, right here would give you a predominantly this H2CO3 form. If you have a pH that's above 6, you would have predominantly, well, above 6 and below 10, you would have predominantly this form right here. And if you have a pH above this number, then you'd have predominantly this form. Okay. So, right here was predominant species present at 7. Well, you're between these two, so this would be your predominant species. And so you put HCO3 minus. Very good. The next thing you do is, there's several ways you could do this next problem. You could, of course, just do it as an ice problem. If you remember your ice problems, which is good to review at this point, because when you do multi-species stuff, you're going to need to understand those better. But frankly speaking, in this case, you have such a large, you are plenty fine just using the Henderson-Hasselbalch in this case. You're not going to have any problems with that, because these are such small numbers. Keep in mind that's a negative log of the value, so this would be like 10 to the negative 6th. So it's very small numbers. So I would start off with the Henderson-Hasselbalch. That's usually the easiest way of doing this. And that's actually right here. So the pH equals the pKa. You're given the pKa in this problem. Which pKa do you use? Well, you use the one that is in front of this number, because the one behind that number will be your base. And so in this case, you're going to use the pKa that is the, let me see here. Oh, no, I'm sorry. Let me double check what I'm got going on here. Okay. Yeah, you're very close to this number. Okay. So if you remember the legs that we looked at just a little while ago, you would have seen that we have the first area, then we have the second area. Now, if you're close to this pKa, you'd be in the middle, that buffer region, the middle of that, between the two, where they're equal concentrations. If you're closer to this one, you're going to be where you have a little bit, you have mostly this still, but you're going to have more of this. So you'll have these two species. You won't have any of this once you get to the point where it is past the stoichiometric equivalence point of this leg. Let me go ahead and look that up again so I can get that in front of you. There we go. So for reference, because this would be the pH, the pKa of 9 or 10.329 right here. It would be the midway between here and here, which would be pure species. So you're going to be looking at this ratio of the CO3 minus, which is the base, versus the ratio of the HCO3 minus, which is the acid. You're going to plug in the pH here and the pKa from the table right there into the Henderson-Hasselbalch, and you'll solve for that ratio. So right here we have the Henderson-Hasselbalch. We want this ratio right here, so we have to subtract off the pKa. That will leave us with the pH minus the pKa equals the log of the ratio we want. To undo a log, you always take 10 to the power of both sides. 10 to the power of a log, that 10 to the power of would be an anti-log, so it actually cancels out. So we're left with our ratio. On the other side, we have the 10 to the power of the pH minus the pKa. We plug our values in. Our pH is 9.75 from the problem we were asked. I'll hit the X in just a bit, show you again. But 9.75 is the pH they gave you, and 10 is the number 10.329. Man, my eyesight's getting bad. Is from this graphic right here. And so that right there is your pH. And so you solve that, and you should get, if you have these exact numbers, you'd get 0.26 for your ratio. Let me know if you don't understand anything or if you have any questions about this. But again, keep in mind that this really is also can be represented by sort of a titration curve. And in my estimation, that's the easiest way to understand it, is understanding the titration curve very well. And if you understand the titration curve very well, then you can clearly understand the species. And what I used to do is, if I had trouble remembering what I'm doing, I'd write out a titration curve and I just sort of label it and figure out where I am on it. Okay? Anyways, let me know if you have any issues with this. I probably overdid it by quite a bit.